Hello, in this video we will examine the simplest connection between Raspberry Pi 3 and ESP32 by using ESP IDF number 5 and sending simplest analog signal from Raspberry Pi to ESP32. We will be using Python and C++ on the Raspberry Pi and ESP IDF C version number 5 on ESP32. Regarding our hardware connection, we will have two pins connected. First one is pin number 7, which is GPIO 4 on the Raspberry Pi, to the pin number 5, GPIO 36 on the ESP32, and we will have a common ground. In more detailed scheme, you can see the ground connection over here, and you can see the pin number 7 here. You can see it from here on the Raspberry Pi connected to the pin number 5, which is GPIO 36 on the ESP32. Similarly, we will running Python and C. I will show two versions of sending an analog signal to ESP32, and we will read this analog signal. Regarding our resources, I want to point out that on the expressive side we are using the resources regarding analog reading, which is relevant to version number 5.2.0, and we will using it on version number 5.0. This is important because on the previous versions and the previous video that we have published, like a year ago, on the version number 4.3 or 4.4, the analog reading was different. So in this resource, you can see the different approach to analog reading, which was implemented in our code. Mostly it's here, okay? All the codes that will be used in the videos are available on the GitHub, and here on the free RTOS ESP IDF 5 with Raspberry Pi 3. Here you have 3 programs. The first one is CPP file, which is running on Raspberry Pi. The second is the Python file, which is running on Raspberry Pi. And the third, the C file, which is running on ESP32. And here everything is written, so it's pretty convenient. Now, what we've done, we took this code here and put it in this one, which basically receive analog input of the ESP32 version number 5, and pasted it inside the project here. So we have standard project, and we pasted this C file inside the ESP IDF project. In parallel, we have a Linux screen here, which we could see, I hope, in parallel to our execution. Here you can see the Raspberry Pi screen, and here you have a VS Code open on the Raspberry Pi with the Python code, the same one that we have seen in the GitHub repository. And here you have an execution window. Similarly, we have the C code here on the Linux, and it's everything working online. which we will execute here. So first we'll run the ESP32. You see, this is ESP32 screen on my PC. We will compile it. We are compiling the project which we have on my PC, and the ESP is connected with the USB cable to my PC. Okay, now we can see that we have the voltage reading which runs every second. This is a file. We have a voltage reading, and every second we have a voltage reading number 5 volts. How it was achieved? First, because of the version number 5, we defined the handler and the one-shot unit here, initialize it, and then we have a reading, ADC one-shot read. We read it, transfer it to the voltage, and print it on the screen every second. This is a program that's running on the background on the ESP32, and this is a serial screen on my PC. In parallel, we will run the Python file. Let's try to do it. Okay. Python. Copy. Paste. It's not working for some reason. Okay, let's open another window. Okay. Let's try here. Oh, it's working. Okay. Okay. We have a Raspberry Pi now running with the Python file, and you can see this Python file here, where we initialize time and GPIO library, and set the mode of the board, which have the board numbers. So we set up the pin number 7 on Raspberry Pi, like GPIO out, and every 5 seconds we put it to high and to low values on the Raspberry Pi output. Similarly, you can see that when the values are high, like now, you have a high voltage here on the, I will use another cursor, and when the voltage are low, the numbers are low here. The interesting thing that in Python, it took me like 10 times faster to implement this code, because it's 10 times simpler than in C++, but the program execution in real time, it's not so smooth. For example, you can see that low and high are jumping together on the same, and the results on the hardware, they're pretty good. Like you'll see, like 5 seconds and 5 seconds, 5 seconds and 5 seconds, but on the screen it's a little bit jumpy. So let's see, it works from the Python, and we send from Linux to the ESP32 5 voltage zeros and 5 volts every 5 seconds. Now let's try the C++ version. So we will kill this process, And now we will compile the C++ file on Raspberry Pi in Linux. Okay. The file is compiled. Now we will run the Linux C++ file. It is the same file, and it's having the same functionality. It's like low, and you see it's low here, high, and it's high here, 5 volts. The interesting thing is that in C, it's much more robust. You see the execution, and the execution on the screen are very consistent, and when it's low, the latency is minimal. It took me 10 times more time to implement it, but it works significantly better in real time in C++ program. How this program is working on C++ with the same functionality like on Python. We have the basic includes when we are using a GPOD library for GPIO execution. Here we initialize the GPIO chip 0. We took the line number 4, which is appropriate to pin number 7 because it's according to GPIOs in this setup. We define the request, which is the line number GPIO number 4, pin number 7 is direction output, and the flags are 0, and then we initialize this request. Then we run an infinite loop. When we put it one time high, sleep for 5 seconds, and then low and sleep for 5 seconds. Basically the same functionality, which is working much more smoother than in Python. So to summarize what we have seen here, by the way, I checked all those values on scope, and it's working good. To summarize, what we have seen here is the connection between Raspberry Pi and ESP32. We connected those two pins. We have an analog voltage for 5 seconds from Raspberry Pi by using Python, and then by using C++. And then we read this analog voltage on ESP32. Thank you.